Hello again. Tonight's going to be a short one. It's related to the ESA Gaia probe and the observation that it found about there being large waves of moving stars in the disk of our galaxy, and how that's really seeing something big by observing a lot of something small. So I've on several presentations taken looks at collectively small things that can result in large scale changes, like picking off electrons from virtual particle interactions being used for large scale power generation, and how radiation reflection pressure can be used as propulsion for space probes and satellites. And the inverse of that is also meaningful, which is you can have large effects that result from very small changes over collectively large areas or quantities. So where this started from was ESA Gaia probe's observations and postulating large-scale wave effects in the disk of the Milky Way. The role of Gaia in that is significant, but what's more important to take away from that is how the large-scale data collection empowered the conclusion they came up with, and how you can apply that to other circumstances. Basically, if you look a lot at individually small stuff, collectively you can realize large-scale effects. So here's the one slide about Gaia and what it did. The European Space Agency, that's the ESA, they had a probe up until earlier this year that was at Lagrange point 2. That's kind of the same area where JWST is. It's about 1.5 million miles from Earth. It's out beyond the moon in the sense that as the Earth goes around the sun, so did Gaia, and Gaia would do a virtual elliptical orbit around L2. So as the Earth went around the sun, Gaia would also be going around the sun and would point out to space from its place at L2, and it would do surveys of just millions and millions of stars and locate all of them, catalog them, and check their locations relative to each other over a period of years. And what they found out was they're moving. Now, it wasn't unknown that they were moving because stars move around a lot. They're in various motions. And from a distance, over the large scale nature of the galaxy, they move very little. Astronomical catalogs are only updated about once every 10 to 20 years because the movement is so slow that if you just take the catalog entry from 2000, you can probably get it in the field of view and then just adjust it slightly. At the end of its mission, meaning it ran low enough on fuel that maybe its orbit would destabilize, they moved Gaia from L2 to a long-term parking orbit with the Earth around the sun. So Gaia is still around. They just shut down the operations of it, laid off everybody. What Gaia would do is periodically just take mosaic pictures of as much sky as it could take, and then it would catalog all the stars and then compare them. So if it took a picture and then came back months later and took another picture of the same area, they would triangulate all the stars and see how they moved. Very tiny fractions of an arc second movement for each image. Over the years, you could actually see the various vectors of which way stars were moving. If stars were in a binary pairing, it could actually see which star is orbiting which other star. They're moving relative to each other. What they really recorded that came across as the amazing conclusion is if you look at all the stars that it cataloged and all the movements of all those stars, then what you see is wave action in the disk of the galaxy. Now, this picture at the bottom is an exaggeration and it's an artist's rendering because the Earth is not out beyond the edge of the galaxy. So this is an artist's rendering of the data that we had. They glued together a picture which would be the disk of the galaxy. Where is Earth in this picture? I don't know if it's on the left side or the right side, but it'd be about 2/3 of the way out from the central supermassive black hole. Now, the arrows pointing up and down is the collective observed movement, and the height of the arrows is the relative speed of that movement. So you can see that different parts of the plane of the galaxy have different levels of movement and different amounts of speed, velocity of movement. Some of the movement of the plane of the galaxy, they are alluding to maybe over the billions of years, the Milky Way has interacted with other small galaxies like the Large and Small Magellanic Clouds, and this shearing velocity affected the disk of the Milky Way, and therefore you have this wobble. Whether you know it or not, the sun bobs up and down in the plane of the Milky Way over 250 million years or so. Not something you're going to notice in your lifetime or even your children's lifetime, but over the history of the Earth in various observations, probably involving, rocks or ice cores, they've observed the bobbing of the sun up and down through the plane of the Milky Way. And if you take that over the hundreds of billions of stars in the Milky Way, you can now see by all their individual movements a wave action going through the disk of the Milky Way. It's not as exaggerated as the length of these lines here. It's much, much smaller than that, but that's what Gaia discovered, had peer reviewed, came away with a conclusion. Yep, there's some wobble wave action going on in the disk of the Milky Way. There was a postulation that this wave action did exist because we knew the sun bobbed up and down, but they had no evidence, no data, no observations to back it up. So Gaia provided the data, but somebody had to say, I think we ought to spend the money to do this. People in ESA had to be willing to go up to the agencies and say, we want to spend, about $1 billion over the next 20 years to, design, build this spacecraft, get it launched to L2, operate it on station at L2 in a virtual orbit for multiple years, collect petabytes worth of data of all the star positions over time, and then run an analysis of that. And that takes people up front, behind the scenes, and after the fact to do all this stuff just in the name of scientific curiosity. So the result is not something you're going to see in an image, not something you're going to see over a short period of time. It's not something that individuals are going to see through their amateur telescopes, but it was postulated. It might take eons, not personal lifetimes, to confirm this, but by having Gaia look at this, those very, very small changes over the life of the Gaia probe could say, we're seeing this moving this way and this moving this way. So it can plot those velocities. If you want to see something that is kind of analogous, think of the old frog in a pot of water and turning up the heat slowly. The frog doesn't realize it until it gets significant. So if you're just looking at these slow movements of stars individually, it's minuscule. Even looking at parts of the galaxy, it's still minuscule. But if you look at it over the whole of the galaxy over a number of years' time, now you can see the effect. But most people will say, well, until it affects me personally, why do I care? Scientific curiosity versus I've got a life, I've got a family, I've got a day job. Those are important. Fine. But there are people that do have a day job of scientific research. You don't need the funding for that. Maybe we'll show you the results when we're all done. But in the meantime, let us get on to the work of scientific research. And why would I want them to spend money on it? Awareness. We'll get to a particular aspect of that. They used to say the same thing about weather up until, late 1920s in Florida, when they had a massive hurricane that kind of showed up out of nowhere. And we didn't have the South Florida Water Management District back then. So a lot of people didn't survive the hurricane due to the flooding. We put in place water management. If you look at some of the places that get a lot of sudden rainwater and don't know how to deal with it, they probably don't have something that is large scale as the Florida water management districts. And there's more than just the South Florida, there's the Central Florida and North Florida. When they started to look at weather involving hurricanes and we could put satellites in orbit, I guess the first time they saw a hurricane from a satellite's perspective in orbit, they went, look at that. We can see it moving. We can see where it's going to be going. We can see how big it is. We can see how intense it is. Let's spend money on the Department of Commerce, which has this organization called NOAA that monitors the atmosphere. We'll put these geosynchronous satellites in orbit, and now we can see hurricanes. So all those interesting pictures in both visual and infrared that you see of storm fronts moving around the Atlantic and Pacific, those are courtesy of GOES East and GOES West satellites. Sometimes what you can't see up close can affect you in the not too distant future. And maybe it makes sense to spend money to do some research there. In summary, until we go to the effort to postulate, create instruments, observe, analyze all those minuscule effects to see if there's some large-scale effect, it'll just go unrealized, maybe postulated, certainly unconfirmed. So you can observe things that are individually insignificant. You can ignore them because you can't sort of add up the large scale effect. Or you can have a large scale effect that, because it's not something that affects you personally in a short term, there's no perceived justification for observation. It's why science has to fund intellectual curiosity, and that's significant because, as I like to say, you never know how much you didn't know until you know what you didn't know. So if you don't expend the funding, make the efforts to create the instruments, to observe them, to analyze the results, to come to a conclusion, you'll never know what's going on out there. Is it important to know what you don't know? Sometimes. Like there was a curiosity about maybe there's a lot more asteroids out there that have Earth's name on it than we thought. Why don't we put together some NASA programs for Earth planetary defense, looking for these things? I think when they found that there were many thousands of Earth crossing near Earth objects, both comets and asteroids, and then they said, well, when will the Earth be at that point in its orbit around the sun where there's a greater than 5% probability that the Earth and this thing might coincide? It might hit the Earth. Okay, they're certainly in the hundreds now, but they're not soon. There may be something that your long-term offspring might be interested in knowing about, but we have to do the research and the observations now. Even though the hazards are off in the future, maybe it makes sense to start spending for it now. And then if you want to know about Gaia, about the large-scale waves in the disk of the Milky Way, there's a similar one that's smaller scale around Orion called the Radcliffe Wave. And then if you want to know about the GOES satellite systems and the U.S. Planetary Defense Coordination Office, there's an acronym for that, PDCO. Okay, how many had heard about the galactic disk wave that Gaia detected? I'm thinking nobody knew about this one. That's good. I always like to bring new information to people who like, I got a day job, I got a life. Sometimes these things just go by. You don't worry about it. That's what I'm here for, is to like consolidate the news and the information and do it.
I'd like to see that picture again of that disk. I have some questions about it. I'm sure you answered it. You did very good. But I didn't follow some of it, and I wanted to make sure what I was seeing. You do really well with pictures, telling me what they mean. And I know, first off, I know it's an artist drawing. I know it's an artist drawing.
Yeah.
But I'm trying to picture now. That is the sun in the middle.
No. That's the center of the galaxy, not the center of the solar system.
The center of
the Milky Way galaxy.
Okay, so we don't see the sun on this.
No, the sun would be a little tiny dot.
Okay, now the arrows going up and down are representing stars.
They're representing the movement and the velocity of the stars.
Okay,
so the arrow is going up, the star is going up in the disk of the galaxy, the plane of the galaxy. If the arrow is going down, the star is going down.
So is this line?
If the arrow is long, then the velocity is high. If the arrow is short, the velocity is less.
Okay. My question is this line that's drawn there, that's they're saying that's a disk right there? Or is that like
the thing that you see
rendering? But I'm trying to figure out what the line is, the start of where the stars are at, and that they're going up. Where are they going up to?
Okay. The length of the arrows is an exaggeration.
Right.
Okay.
I got that.
The line going, the like Ripley line going through the center that goes blue, red, white, black, has the central glow.
Okay, that's what I want to know about.
That's the plane of the Milky Way galaxy.
But it's not a solid plane. That's looking like it's solid, but it's not really solid.
No, there's like 200 billion stars in that little line.
Okay. Now, how come there's nothing going up and down in the middle?
Because there's a supermassive black hole that's holding it all in place.
Oh,
as you get towards the ends.
Okay, I'm sorry, I missed that.
As you get towards the ends, towards the edges of the galaxy, now you can start to have other effects that the supermassive black hole can't like constrain.
Now, the ones that are going down on the right-hand side.
Yes.
They went exaggeratedly down
Well,
compared to other.
the length of the line is exaggerated. The amount of measured velocity from Gaia is very small over multiple years.
So is there some part of the galaxy that's affected differently than the
Yes.
other part of the galaxy, as they're saying here?
Yes, that's what they're trying to say, is that it's not just if everything on the left was moving up and everything on the right was moving down, then that would say the disk of the Milky Way is kind of flipping around. But by it going up and down in these wave actions, what they're guessing is that the Milky Way galaxy has, over billions of years, interacted with other galaxies, and therefore it's induced these waves in the disk of the galaxy. And the waves that you see here are the reverberation results of those wave effects on the Milky Way.
From the other galaxies?
From other galaxies that the Milky Way might have even absorbed.
Oh, so now they might be within our galaxy.
Yes, the stars from those prior galaxies have been absorbed by our galaxy, but the movement of that galaxy as it sliced through the Milky Way, that movement is still rippling.
I wonder if it's damping down with time.
Yeah.
We'd have to look at these observations. We'd have to have a Gaia that lasts decades to see if we can see the movement. We can tell that it's moving, but is the movement accelerating, decelerating? But if we don't put another Gaia up there, we won't know. Remember the original, I guess, statement of what dark energy was they observed the stars on the outer edge of the Milky Way as moving at not too different a velocity than the stars closer into the center of the Milky Way. And they were saying that something is accelerating those stars at the outer edge of the Milky Way. Much like you see the velocity changes here, could it be that what they were looking at was nothing more than reverb accelerations, and it only looks like they're keeping up because they've got other things that have induced velocity changes in them? It's current observations. We won't know more until we look more.
And there was something that happened here on Earth that we thought that there was something out there going on. We knew there was a wobble. You said something about
we knew from measurement of the sun against background stars that the sun over time bobs up and down in the plane of the Milky Way. We don't quite know why it does that, but it does that. And it takes about 250 million years for a complete bob up to bob down.
Okay.
A complete sine wave curve.
And this explains it?
No.
It helps to explain it somewhat?
It may be a completely unrelated effect. We have no data that ties it to this.
Oh, but you brought it into the conversation.
Because over 250 million years, if you went out tonight and said, is the sun any higher or lower in the disk of the Milky Way than it was last night? Not at all. It's a very, very small change that over a long period of time will have an effect. Much like precession of the North Pole. The North Pole currently has Polaris as the North Star. It's not precisely at Polaris. It kind of circles around Polaris. And over the next few hundred years, it won't be Polaris. It'll be moving off of Polaris, heading towards a different star.
So are you saying that the sun bobbing up and down,
yes,
is reflected in this, but does not mean that the stars moving on it have anything to do with it? Is that the...
No. The sun bobbing up and down is not reflected in this data. It's a different movement, just like precession is a different movement. In space, things are moving every which way all at the same time.
Everything is moving. Yeah.
Not everything is moving. Everything is moving in different directions at different velocities all at the same time.
Nothing is standing still.
Nothing is standing still. There is no up and down.
Drives me crazy.
Yeah. Remember, the thing to take away from this is if you look at a lot of small stuff, you can discern big stuff if you look at a lot of small stuff over a long enough period of time. Things that you think are minutiae, if you collect enough of them over a long enough period of time, you get large scale things. Okay.
That's when the people are complaining that, oh, we have so much data that we can't figure out anything because there's too much.
Well, there is the concept of, like the Rubin telescope in South America, is collecting maybe 5 petabytes of data per year. That's the data that they're keeping. What do you do on the second year? Where do you go find another 5 petabytes of storage? Now remember, you have kilobytes, megabytes, gigabytes, terabytes to peta. But the amount of storage required gets to be entire, like buildings full of nothing but servers with storage. We can only increase the storage density so high. If you look at these new data centers that they're building for AI, the data center is so large that its power draw is greater than the local cities that they're putting it in, and its water draw for cooling is greater than the local water supply. So when they're building these enormous AI data centers, they have to build their own power generation plants, and they have to basically do their own water purification plant. The water you drink can be dirtier than the water used to cool the computers. Because remember, computers have metal plumbing in them, and you don't want to be putting water into there that's going to be too acid or too alkaline, because it will corrode the plumbing. So think about that for a moment. The water used by the supercomputers for cooling is purer water than like the government standards would be for you drinking the water.
Monroe, did you see the video that came out last week about them build? I think we the algorithm pegs us as being pretty similar,
Yeah.
except they keep trying to sell me private jets. But I don't quite get that. Maybe you saw the video about the XAI mega computer that they're building in what's north of Mississippi, Tennessee.
Yes, I did see that.
Yeah. That's amazing that they built their own power plant in Tennessee, and then they bought a chunk of land in Mississippi and bought a power company in Europe and shipped all the gas turbines from Europe to start the other half of the gas plant in right across the border in Mississippi. It's astounding.
They had to disassemble the gas turbines, create packing crates for them so that they could be shipped long distance intercontinentally, and then brought in and reassembled in place and get working again. So you can just see like the millions of dollars walking out the door for the enormous scale of effort they had to put in to do this. But if they didn't do that, they could not run enough computers because they wouldn't have enough power, and they couldn't run enough computers because they wouldn't have enough water to cool them.
Astonishing. More power than for a whole city. Somebody. Do we just need to wait for somebody to prompt AI to end human suffering, right?
No. See, I think if we want to solve the power problem on this planet, we just have to let the AI data centers grow to like 1,000 times bigger. They'll solve the power problem. They'll find virtual particle interactions that produce loose electrons, and they'll gather those in no nuclear, no fossil fuels, no wind turbines, no solar, because they need far more than that. So they will produce solid state power generation facilities that are probably tens of gigawatts of capacity, and they'll fit like on a city block. But they have to get to the scale where current solutions are not a solution. Right now, they're in the, if I spend enough money, I have a solution. When you get to the point where it doesn't matter how much money you have, you can't solve the problem. You need to solve the physics problem first. And it won't be through, modular nuclear reactors. It'll be through understanding the physics well enough to know how to get electrons out of nothing. They'll do it. They just have to have data centers that are about 1,000 times bigger, and then they'll solve their own problem. And as far as the heat goes, it surprises me that they're still using water for cooling. If you think about an electric vehicle, the better ones have regenerative braking. You expend electricity to get the vehicle up to speed, and then when you want to stop the vehicle or slow it down, you step on the brake, but it doesn't apply the brake pads right away. First thing it does is it converts the motor into a motor generator, and it takes the electricity, and by virtue of using the wheels as generators, it induces resistance to the magnetic field, and therefore it slows the vehicle down while producing electricity that it sends back into the batteries. You can do the same thing with heat. If your computers are producing too much heat, make more efficient Seebeck power generators. It's the same thing that thermocouples do on board the deep space probes like Voyager 1, Voyager 2, Perseverance, and Curiosity, except they use plutonium for the heat. In this case, you'll use the waste heat from the electronics to produce the heat that can kind of act like regenerative electricity generation. You take the heat, convert it back into electricity, you put that back into the battery system, and now you're draining heat off without the heat having to go somewhere. When you're using water for cooling, the water goes into plumbing. The water gets near the hot computer chips. It takes heat off the computer chips, puts it into the water, and now the water's got to go somewhere and be cooled down. You didn't make the heat go away. You just moved the heat somewhere where you got to move the heat away. Where's the heat being moved away? Well, they're going to spray water into plumbing that's going to transfer the heat out of the water-cooled plumbing into the air. If you ever see these giant funnels around big power plants, they're taking the heat from the power plant, be it nuclear or gas turbines, they're taking out the heat, putting it into water, and then they're spraying the plumbing with more water to cool down the plumbing, and that produces water vapor, which goes up out of the stack and adds heat to the atmosphere above the plant. So it doesn't make the heat go away. It's just like, we're going to put it up here where we don't have to worry about it. That's not a solution to the problem. But I'm a systems guy, so when somebody says, we've solved the problem, we're just going to build our own power plant, where are you going to get the fuel for it? Natural gas. Okay, you're now going to need how many millions BTUs per year of natural gas? Where are you going to get that from? The local community probably can't let you use their residential and industrial natural gas lines because you'll suck them dry. Oh, we're going to be piping the natural gas in from Canada. How's Canada feel about that? Or we're going to have a ship dock at the biggest seaport nearby, and we're going to transfer onto tanker trucks the natural gas. How many tanker trucks will that be? So whenever they think they've solved the problem just by injecting money into the system to scale something up, they haven't really solved the problem. They just made it a bigger problem. But that's just my jaded viewpoint on things from having looked at this stuff. First time I looked at a large scale system was the cooling canals of Turkey Point in Southeast Florida, and going like, where isn't the heat just going to go up into the sky?
They should send it to bathtubs so people could take baths.
You know, in countries that have a lot more winter time, almost year-round winter time, they actually take the heat from systems and use that as a heat storage and then run it through water plumbing back to homes and businesses for them to heat their homes and businesses in the winter months. So you think about, okay, Florida Power and Light provides electricity for South Florida. If you were up in the Arctic Circle and you needed not only power, but you needed heating, you wouldn't go buy oil for your burner or natural gas. You would subscribe to the local heating service, and they would put a plumbing line into your house or your business, and you'd go through radiators and blow air over them and take the heat out of the water, and you would heat your facility.
And New York City supplies steam to a lot of big buildings there.
In New York City, there are actually steam suppliers, because a lot of industrial processes and machines, they're not just air driven, they're steam driven.
Yeah.
Because during the industrial age, a lot of things were steam driven. So all the plumbing is there. So yeah, services. If you have the services, use the services, because that's probably a lot cheaper than reinventing that wheel.
So Monroe,
yes.
When you said a few minutes ago, there was no up, there was no down, there was no side by side.
Yes.
Were you just referring to the Big Bang, or were you referring to the actual poem?
No, I was referring to the fact that whatever you think of as your place of reference somewhere in the universe, that's your up and down.
Okay. Then let me tell you.
They have a different up and down.
There's actually a poem about the Big Bang that starts with those lines. There was no up, there was no down, there was no side to side. So anyway, I sent you the link to that. So sometime in the week, take a listen. It's truly amazing when they encapsulate so much in one minute poem. It's amazing. I texted
you. Oh, a text. Okay. I will take a look at it over time. Right now, I'm working on the altitude azimuth computerized radio telescope mount, doing all sorts of things with that. And I'm also working on the vacuum pyritohedron buoyancy craft. I produced an Excel spreadsheet to, if I scale the sides of the carbon fiber rods, how much more vacuum can I get out of it versus how much heavier it will be, how much larger it will be. And so now I've got basically an Excel workbook that has a spreadsheet in it that I can plug in numbers and go, what if? Okay, any other comments or questions before I stop recording? Hearing nothing.